Okay, this is the section that you've been waiting for a long time. We've been hinting at some of these rules for finding the derivative, and now we're going to truly get into them. So in this section, we're going to look at two major rules. First, we're going to look at the derivative of a constant, and then we're going to look at the derivative of a power function, like x squared. Okay, so we do need to prove each of these. So once we prove it, then we can start using them. All right, so let's first look at how to find the derivative of a constant function. Okay, so we're finding the derivative of a constant function. Okay, so I'm going to come back and I will fill in the answer to what the derivative of a constant function is, but let's first think about an example. And I think this example is going to lead you towards what the derivative of a constant is. Let's say we have the function f of x equals 4. Okay, let's graph that function. That means I'm going to have a y-intercept at 4, and it's going to be a horizontal line. What is the slope of this tangent line going to be? It's going to be a slope of 0. So the derivative of this function is 0. Now all constant functions are going to be horizontal lines, so therefore the slope of the tangent line is always going to be 0. So therefore we can conclude that the derivative of any constant function is always going to be 0. So here's how the definition works. It says if f is a function with a constant value, and we'll call that value c, then we can conclude that the derivative of f, which is the same thing as taking the derivative of c, is always equal to 0. So the derivative of any constant is always 0. Okay, so now we have an example. We have an example over here. We have the theorem or the statement. Now let's prove this idea. Okay, so we're going to take and prove the constant, the derivative of a constant function. All right, so we're going to go back to our original definition to prove this. I'm basically trying to prove that the derivative of a constant value of c is 0, is what I'm looking to prove. All right, so to prove that, we're going to go back to our limit. We're going to let h approach 0. We're going to use our definition of the x of x plus h minus f of x over h. Okay, so our f of x, our function that we're going to start with, is just some constant value c. So if I plug 8x plus h in, it doesn't matter what x plus h is. If I plug it into c, it's just going to be c. And if I plug x into c, it's just going to be c over h. So then I'm left with a limit as h approaches 0 of 0 over h, okay, which is 0. We've just proven that the derivative of any constant is 0. Okay, so that one isn't terribly exciting, kind of common sense. The next one is going to have huge implications in being able to find the derivative. All right, so let's go into this one. This is going to be what we're going to call it the power rule. Now, first we're going to just look at the power rule for positive exponents. Positive integer powers of x. Positive integers powers of x. Okay, so things like x cubed. All right, so here is the rule, and we're going to see how it kind of comes out. I'm just going to state it here. We've already talked about it a little bit, but here's the rule. Okay, the rule says take your exponent, put it out front, okay, then take your base and subtract 1 from your exponent. That's it. Okay, so we're going to look at an example here. Okay, we're going to use the definition first. We're going to look at the function f of x equals x cubed, and the question is what is the derivative? Okay, I want to know what the formula is for the derivative. All right, we're going to use the definition first. So if we use the definition, this is going to be the definition of derivative here. We've been doing this a lot, so I'm going to do it one last time. So we're going to use, the limit is going to be, as h approaches 0, of f of x plus h minus f at x over h. Okay, so if I do the limit as h approaches 0, it's going to be x plus h cubed minus x cubed over h. Okay, and that's going to be the limit as h approaches 0. All right, so cubic, we know this is a mess. So it's going to be x squared plus 2xh plus h squared times x plus h minus x cubed over h. Okay, and then that's going to give me the limit as h approaches 0 of, let's see, that's going to be x cubed plus 2x squared h plus xh squared plus x squared h plus 2xh squared plus h cubed minus x cubed. Okay, all over h. All right, so now when I go to clean that up a little bit, let's see, the x cubes are going to cancel. I'm going to have a 2x squared h and an x squared h. So that makes 3x squared h. I'm going to have an xh squared, and I'm going to have 3 of those. So I have 3x squared h. I've got that. And then I have a plus h cubed all over h. Okay, so then when I go to take out the limit, as h approaches 0, I'm going to take an h out, and that's going to leave me with 3x squared plus, oh shoot, I screwed this up a little bit up here. It should have been, this should have been h squared. Okay, so that's going to be 3xh plus h squared. Okay, all over h. And now the h's are going to cancel. So I'm going to be left with a limit as h approaches 0 of 3x squared plus 3xh plus h squared. Okay, so now I can substitute, and h are 0, so I get 3x squared. Okay, so there's a derivative. The derivative is 3x squared. So let's go back, and now let's prepare to use our power rule. If I had taken the power rule says take your function. Here's f of x equals x cubed. Bring the, according to the power rule, it says the derivative is you bring the 3 out front, and then you subtract 1 from the exponent. 3 minus 1 is 2. Same exact answer. 3x squared here